Well, in Lecture 27, we're going to take a look at even more ways of defining function-like things, objects, lambdas. We can define function objects of our own. We can use predefined function objects. These are mostly intended to be useful with algorithms. So let's dive into this. So a function object basically is any object that makes use or that implements the parentheses operator. Okay? So we have defined for some of our own classes, like the binary tree class, the singly linked list class, we have defined operators like assignment and is equal to, and the insert operator, the put to operator, the double less than symbol. Turns out we can also define the function call operator. And if we create an object that supports the function call operator, or if we create a class that supports the function call operator, then any object of that class can be used as a function. And in particular, it can be used in a function in algorithms like for each or transform or various other algorithms. So here is an example. This is a file that you can look at in the example code files for Lecture 27. We have a class named addN, and this class is incredibly simple. It supports exactly one constructor. You're required to pass one int argument to the constructor, and all the constructor does is to initialize its one and only data member n with whatever the argument value is. All right? So within an addN object, the only data member is n, and all the constructor does is to establish that value for n based on the argument that was passed into the constructor. The other member function that we have is the function call operator. Okay, so we define the function call operator just like we would define the assignment operator or the is equal to operator. We say the word operator followed by open and close paren. Now, following the open and close paren operator, we also have the usual parameter list that any function requires. So this may look pretty strange that we have open and close paren followed by another set of open and close paren. The first open and close paren, that's the name of our operator function. The second open and close paren, those are the parentheses containing the argument. And all this function call operator does is to compute the sum of the value passed in plus whatever value is stored for n. All right, so I think that's confusing enough. Let's see it in use. Continuing on, in the main function underneath this class, I'm going to create for myself OStream iterator 1 so that I can conveniently display things to the screen with the copy algorithm. And I'm setting up for myself a vector of 6 values, 4, 7, 1, 3, 4, 9. All right, so this first copy algorithm just displays those values, 4, 7, 1, 3, 4, 9 with spaces in between. Now I am creating a variable try again. I am creating a variable named add3 that I'm initializing by invoking the constructor addN with 3 as the parameter. By the way, I could have accomplished the same thing by saying add3 equals addN3 or add3 and then curly braces addN3. So I'm using the parentheses here as one of the 3 mechanisms that I can use for initializing the value of a variable. All right, so add3 is a variable. I'm initializing it by invoking the addN3 constructor. And I'm letting the compiler figure out what the data type of that thing is by using auto. And then I'm using a transform operation, and I'm passing in this add3 object that I've just declared. All right, so since this add3 object is an object belonging to the addN class, and it supports the function call operator, I can use transform to add 3 to each of the elements, starting from VB up to but not including VE, with the results going back into VE. So the upshot of this is that I will have added 3 to each of the element values in the vector V. All right, so in this blue example, I created a separate addN object named add3, which I then passed as the fourth argument to the transform algorithm. I don't really need that variable for any reason. I can go ahead and just call the addN constructor as the fourth argument to transform, and that will create an addN object in which the little n variable has the value -6, and so this transform will subtract 6 from all of the values in VB. Okay, so that's the end of that, and the output is shown here on slide 5. Let me do this live so you can see it. So here is the what is the name of this program? addN test. Okay, here is the addN test file, addN test.cpp. There it is. Contains what we talked about. And I'll run it, or compile it. G++-O addN test addN test.cpp. All right, it does compile, and it does execute, and it does show the result on slide 5. All right, so that's creating your own classes that provide function objects. In the library, there are a ton of predefined function objects. To use these, you have to include the functional header, and there are arithmetic functionals, relational functionals, logical, and also some bit-oriented functionals that we won't bother with. Here are the arithmetic operations. We do have a unary negate functional, which simply takes each incoming element value and replaces that value, and returns the negative of that value. So let's take a look at that first in a code example here. Okay, so here we have a file called functionaltest.cpp. I'm setting up my output stream iterator so that I have spaces between the values. And then I'm creating this vector v1 with a bunch of values in it, and I'm using copy to display those values. I'm also creating a vector of integers called v2, which I'm copying from v1. Now here, for the first time, I'm using an algorithm that I briefly mentioned, but that we haven't seen before. Random shuffle will do a random shuffling of all of the values within this vector. Random shuffle requires what are called bidirectional iterators to be able to work. But fortunately, the iterators that we have for a vector are bidirectional. That is, you can count forward and you can count backwards. So I'm going to end up displaying v1, and then I'm going to end up displaying the shuffled copy of v1, which we're calling v2. So that's the first thing that's happening. And then here I'm using the negate functional. Now, this notation may look a little bit strange. Negate int, that's a data type. Negate int with parentheses after it invokes the constructor for that data type. So it creates an object of type negate int. And this is a unary operator. So here I'm creating an output vector v3 initialized with all zeros. It's the same size as v1 and v2, but it's initialized with all zeros. And I'm saying, let's go through v1 from beginning up to the end, and let's put the negative of each of those values into v3. So that when I then display the contents of v3, what I should have in here are the exact negatives of all of the values in v1. All right, so that's one example of a predefined functional. Now, notice that these other arithmetic functionals are binary functionals. And we haven't talked about how to deal with binary operators in our algorithms yet. Okay, so these are the arithmetic binary operators. There are also equality, inequality, relational, and logical operators. Most of these are also binary, except for the logical not, which is a unary operator. Here is how we deal with binary operators with the transform algorithm. It turns out that in the transform algorithm, in addition to giving one input vector by specifying the begin and end iterators for that, I'm sorry, I should say input container. Our particular example here is a vector, but here we're giving the begin and end range iterators for the container that we're getting from. We can also give a second input container. Following that is where we specify our output container. So notice the difference. In the transforms that we've been using up until now, we have had 1, 2, 3, 4 arguments. We've had the first two arguments are assumed to be the begin and end iterators for the input container. The third argument is assumed to be the begin for the output container. And then the final one is the functional that we want to apply, which has to be a unary operator. But if I give 1, 2, 3, 4, 5 parameters to transform instead of 4, remember that we can do overloading in C++, and so the compiler is able to tell the difference between the version of transform that takes 4 arguments versus the version of transform that takes 5 arguments. And so if we give 5 arguments, the compiler calls the version of transform that takes a begin and end iterator for one input container and the begin iterator for another container. Now that container has to have at least as many values as the first container does, because we will go from v2.begin up through at least as many, or up through exactly as many values as exist in the first container. And the output, the combination, the binary combination of those elements will be stored into this output container, v3 in this case. And the particular functional that I'm using here is plus. So what we're doing is we're saying, let's take the vector v1's elements, let's take the corresponding elements in v2, and into v3 we're going to put the plus of the v1 element and the v2 element. Okay? So that's this guy here. All right, so we take one element from v1, we take the corresponding element from v2, we add those together using plus, and store the result into v3. All right, so whereas v3 initially was just filled with zeros, Yeah, initially it was filled with zeros. Then we put the negative of V1 into V3. Now we're putting the sum of V1 and V2 into V3 and displaying that. This final example, the black example of transform, is using greater as our functional. The idea here is that we take each value from the first container, V1, one at a time. We test whether that element is greater than the corresponding element in V2. Now, greater actually returns a Boolean, but we are storing that into V3, which is a vector of int. And that's fine, actually, because if you take a Boolean value of true and store that into an int vector, true becomes 1. On the other hand, if you take a bool value of false, that becomes 0. So V3 in this case is going to be filled in with a sequence of zeros and ones, depending on whether the element in V1 is greater than the corresponding element in V2 or not greater than the corresponding element in V2. All right, well, that was a whole lot of talking. Here is the output that's produced. And let me go back to the beginning of the of this example program. You can see this functional test code in the example code. All right, so we're creating our output stream iterator, we're creating V1, and we're displaying V1. And there is the output from our black part of the code, and it's just, 47134, 98085, that's the values we put into V1. V2 is copied from V1, but then it's shuffled. All right, so the values in V2 are the same as the values in V1, but they're in a different order. Consequently, by the way, if I use the is permutation algorithm, I could discover that yes, V2 is a permutation of V1 or vice versa. And so in the blue code here, we're just displaying V2. Now, in the red code, I did not bother displaying the vector V3 of all zeros. What we're going to do is to take the vector V1 and store into the vector V3 the negated ints of all of the elements in V1. And so that's exactly what we have. So instead of 47134, we have -4, -7, -1, -3, -4, etc. Then, in the green code, I'm taking the elements in V1. The corresponding elements in V2 are added with this plus functional, and the result stored into V3. So when I display V3, what I have is 4 plus 0 is 4, 7 plus 7 is 7, 1 plus 3 is 4, 3 plus 8 is 11, etc. All right, so V3 here is the sum of V1 and V2, or at least the corresponding elements of V1 and V2. And then finally, with this greater functional, I'm testing whether elements in V1 are greater than the corresponding elements in V2. Well, 4 is greater than 0, so that's true, which gets stored into V3 as 1. 7 is not greater than 7, so that's false, which is 0. 1 is not greater than 3, 3 is not greater than 8, 4 is not greater than 4, so I have 3 more zeros. 9 is greater than 8, 8 is greater than 5, so now I have 2 1s, and so on. So that's what's going on with those examples. Okay, now a lambda expression is even easier to use than function objects or than functionals, and it gives us a way of defining an in-place function that we can call. These are very easy to use with algorithms in comparison with ordinary functions or template functions or functionals or function objects. They were introduced in C++ 11 and are one of the most important enhancements made at that time. So previously we took a look at using the transform algorithm by giving the beginning and ending iterators for some range, perhaps in a vector, and some output iterator, which may be a different container, a different vector, or it may be the same vector, the same container. And we had this template function, add_n, to which we passed this value 5. And that added 5 to each of the elements in the input range and stored the resulting modified values in the output range. Well, this is all very well as long as we remember what add_n5 means. If we have the code for the add_n5 template function handy, we can just refer to that function to see what the thing is doing. But much easier than that, instead of calling this add_n5 function, we can define a so-called lambda function, as illustrated right here. The square bracket notation introduces the lambda. It basically tells the compiler, hey compiler, I am defining a function for you right here. The function doesn't have a name, it's just we just use these square brackets to introduce the lambda. Then we have a parameter list associated with this lambda. In this case, we're just receiving one integer value as our element. And then we have, in curly braces, a body of code, just like we would have for an ordinary function. So really, this just looks like a function definition, except that we don't have the name of the function, and we don't need to bother with a return type, because that's figured out from what the body is returning. All right, so when we apply this lambda to each element in this range from B to E, we pass in the element to the lambda, and the lambda simply computes and returns whatever that element value is plus 5. And the result is exactly what we had happen here with add_n of 5. So a lambda, or lambda expression, is an anonymous function that you just define in line in your code at the point where you would like to call this function. Now, a lambda is part of the language, so you don't need to have any header. You can just define a lambda and use it. To introduce a lambda, you type a pair of square brackets. This is literally called the Lambda Introducer. It tells the compiler that you're in the process of defining a lambda expression, that is, defining an in-place function definition. And you enclose one or more statements in curly braces, as you would do with an ordinary function. So here we have an example of a lambda expression that only contains one statement, namely it displays to see out the string lambda on a new line. Now, this is a function definition, a lambda definition, I should say, and so to invoke this lambda, you use the function call operator on the end of it. All right, so here is where we defined our lambda, and then if we would like to call the lambda, we add parentheses at the end of the lambda, and that will cause lambda and a new line to appear on the screen. Now I just noticed a typo here. This double quote is in the wrong place, so that should obviously be after the \n. Most of the time you do want to have a name that you can use for the lambda, and this is easy to do by using our good buddy auto. You say auto and give the name that you would like to use for the lambda, and that name is then initialized to the lambda definition. And then later when you want to call the lambda, you simply give that lambda name again with the function call operator. Now it's easy to send arguments into a lambda. You can use parentheses between the lambda introducer, the square brackets, and the body of the lambda, the curly braces, to specify the names and types of any parameters that you would like this lambda to be able to receive. Here we're specifying that lam2, the name that I've given this lambda expression, is expecting to be provided with 2 int arguments, and all lam2 will do is to display the values of those arguments separated with a space and ending with a new line. Okay, so I first define the lambda, name it lam2, and then here at the bottom of slide 4 is a call of lam2 with 4 and 8 as the 2 int arguments. It's also perfectly possible for a lambda to return a value. You simply use a return statement inside of the body of the lambda. And in a very simple case, such as this, we've defined a lambda that we've named lam3. Lam3 is taking 2 int arguments, and the compiler knows that if you add an int to another int, what you get is an int. And consequently, the compiler will infer that this lambda returns an int as its value. All right, so here I am calling lam3 with 4 and 7. That's going to return 4 plus 7 is 11. I haven't chosen to do anything with that 11. That is, I haven't assigned it to an object, I haven't displayed it, so the 11 just sort of disappears into thin air. But nevertheless, that lambda does return the int value 11. Now, let's suppose that you want to specify the return type rather than having the compiler deduce the return type for itself. It turns out, for a lambda definition, we have a little bit of a syntactical quandary because the lambda introducer has to be the first part of the lambda definition. That is, the square brackets have to be the first thing the compiler sees when it's compiling the code for the lambda definition. We can't put the return type in front of the lambda introducer, or the compiler will get confused when it reaches that return type. You know, why is there a data type sitting here at this point? So what we use is this frankly kind of bizarre notation of the arrow symbol, that is the dash and the greater than symbol, followed by the return type. lam4 here, just like lam3, takes 2 int arguments that we're calling I and j, and it computes I plus j, but the value is going to be returned as a double instead of as an int. All right, so when I call lam4 with the ints 4 and 7 as arguments, the return value that comes back from that is the double 11.0. Okay, so here on slide 6 and slide 7, we're going to take a look at some simple lambdas and their results when they're called. On slide 8, we will have the output produced by this program on slide 6 and 7. So first of all, on slide 6, we have the first example that we looked at, an unnamed lambda being defined and then immediately called using the function call operator, the parentheses at the end of the lambda definition. And what we see on the screen from that is the black output here, just the word lambda. In the blue code on slide 6, we're giving a name to this lambda definition. We're going to call it lam1, and then we're going to call lam1 with the function call operator, and this time we get lambda again in the output. That's the blue copy of lambda. lam2 is a lambda that takes 2 int arguments and uses those int values for some purpose. In this case, all this lambda will do is to display those values separated with a space and concluded with a new line. So when I call this lambda, which I've named lam2, with these 2 arguments 4 and 8, sure enough what I see on my screen are the values 4 and 8. Then in the green code on the bottom of slide 6, I'm defining lam3 as a lambda. This lambda returns a value. Specifically, it returns the sum of its 2 int arguments. And since I have not specified a return type, the compiler deduces that this thing must be returning an int. Consequently, in this cout statement, when I call the lambda whose name is lam3 with the arguments 4 and 7, that computes and returns an int 11, and I see that int 11 in my output. Then continuing on to slide 7's code, the bottom half of this little program. This time I'm defining a lambda and I'm specifying that this lambda returns a double. Now in this case, I don't have a choice about whether I specify the return type. I have to specify the return type because notice that this lambda definition has two returns. In the first return, in the case where the parameter i's value is greater than the parameter j's value, I'm returning I, which is an int. But if I is not greater than j, I'm returning j times 0.125, which is a double. So here I have a situation where the compiler does not have a basis for deciding what the return type is supposed to be, and I have to tell the compiler, in order for this to work, that this lambda will be returning a double. When I call this lam4 with the arguments 4 and 7, well, i's value is 4, j's value is 7. Since i's value is not greater than j's, I'm going to return 7 times 0.125. That is, I'm returning 7/8, which is 0.875 when that's displayed on the screen. And one more example, this time using some standard functions within the body of the lambda. This lambda, which I'm naming lam5, takes a double as its argument, and it's using some standard functions, cosine, square root, and exponent, so that we get the cosine of the square root of e to the x as our result. When I call lam5 of 2.5, all right, I'll confess that I cannot do this calculation in my head, but what we get out on the screen is minus 0.9398, which certainly makes sense as the cosine of something. Okay, so that's some examples of defining and naming and calling lambdas, some of which take arguments and some of which return values. Now, at the point where you define a lambda, it's very likely that there are some other variables in the same scope where you have defined that lambda. For example, if you've got a function and you define a lambda within the body of that function, then that function may have parameter variables, may have other local variables that are in the same scope as the lambda. Now the lambda can capture, that is, gain access to either values or references to these other objects that are in the same scope as the lambda. And you do this by using various notations in the square brackets that denote the Lambda Introducer. For example, if you put an equal sign inside the square brackets, that means that within the body of the lambda, you would like to be able to have direct access to the values of all of the other objects that are in scope at that point where you have defined your lambda function. On the other hand, if you use an ampersand in the square brackets, that means that you would like to be able to capture all of the objects that are in scope by reference rather than by value. As opposed to capturing all of the objects in scope either by value or by reference, you can constrain which object or objects you want access to by just naming that particular object. So for example, if there is some object j within the scope where you're defining your lambda, you can give j within the Lambda Introducer to indicate that within the body of the lambda you just want to be able to use the value of j. On the other hand, if there's some y object in the scope where you have defined your lambda, then you can access the y object by reference within the body of the lambda if you say ampersand y in the introducer. And you can sort of mix and match what's going on here. For example, this notation here, j comma ampersand y, means that within the body of this lambda, I want to be able to access j by value. That is, I want to be able to read from it but not modify it. But I want to be able to access the object y by reference. I want to be able to both read and modify y. If I use, on the other hand, an equal sign in the square brackets, that means that I want to be able to access all of the objects in scope by value. But here, by also saying ampersand y, I'm saying, by the way, I want to access the value y by reference. Okay? So within the body of this lambda, I will be able to access all of the objects that are in scope at the point where I have defined this lambda. Almost all of these I will be accessing by value, with the exception of y, which I will be accessing by reference. Okay, so if you capture an object by value, that means that you want to have read-only access to that object within the body of your lambda. Whereas if you capture an object by reference, that means that you want to have both read and write access to that object. Now, it turns out that capturing only applies to local variables and parameter variables. Global variables or static local variables cannot be captured according to the standard. It does turn out that GNU C++ allows it, but that's not a portable feature. So you may discover that your compiler allows it in some cases, but you should not rely on that to be true. By the way, when you capture an object by value, the value that gets used for that particular object within the definition of the lambda is whatever value that object had at the moment where the lambda was defined. Okay, this is getting a little too hypothetical. Let's take a look at some examples to illustrate what's actually going on. Here on slide 11, we're using a couple of different capture notations, and on slide 12, we have the output resulting when we run this program on slide 11. Okay, so within main, we have a local int object named I, which is initialized with 4, and we have a local double object named x, which is initialized with 0.125. We're defining a lambda here that we're going to name lam1, and in this lambda, we're capturing all of the objects in scope by value. Now, the two objects that are in scope here are the local variable I and the local variable x. So we're capturing the current values of those objects for use in the body of the function. That is, if I use I in the body of the function, that will be replaced with a 4, and if I use x within the body of the function, that will be replaced with a 0.25. Okay, so when I call lam1 with the function call operator, what I get displayed is this black output. 4 is the value of I at the point where that lambda was defined. 0.125 is the value of x at the point where that lambda was defined. All right, lam2 is capturing I by reference. That means that when I execute lam2, if I is changed within lam2, then that change will be reflected back in I within the main function. In other words, since I is being captured by reference here, and I's initial value is 4, what happens in the body is that 4 gets replaced with 12, that is 4 times 3. 12 is displayed when I call lam2, and then when I display the value of I after lam2 has been called, I'll discover, I has been changed to 12. Okay, so I define lam2, I capture I by reference, I first change I's value to 3 times itself and then display I, so that's the blue 12. Then, in this red cout statement, when I display the value of I get 12. However, that doesn't affect what's going on in the lambda definition where I captured I by value, because when I captured I by value, the value I captured for I at that time was 4. So when I call lam1 again, I still get 4 for the value of I at the time that lam1 was defined, and 0.125 is the value of x. Okay, so finally let's take a look at how we can use lambdas with algorithms. On slides 13 and 14 we have a small example program, and the output is shown here on slide 15. So let's walk through this example. Here I have a local variable named capital N, initialized with a value of 2. I have a vector of int v that's initialized with 7 values, and we'll assume, because I've got my tools included here, that the OStream iterator, OSISP, is available to me. That displays to the cout output stream integer values separated with spaces. And so if I copy v from begin up to but not including end, that will simply display the values that are currently in v. So no lambdas going on yet, we just displayed the initial contents of v. Now, in the green code here, I've specified the definition of a lambda expression, and I've got the name addN for that lambda expression. Notice that in the lambda, we're capturing the local variable capital N by reference, and this lambda takes an integer argument, which we're calling x, and what this lambda will do when it's called is to simply return the argument that's been passed in plus the current value of n. Alright, so now we're going to call a transform algorithm using addN. We're reading from v, from begin up to but not including end, and we're also writing out back into v. So the upshot here is that each value within the vector of int v is going to have 2 added to it. Okay, the argument to the addN lambda is the value that we're reading from v. When we call the lambda with that argument, what we get back is that value plus whatever n's current value is, which is 2. And so the upshot should be, when I look at the result in this green copy algorithm, I should now in v have the same values where each value has been increased by 2. And that's exactly what I see. So 1 got replaced with 1 plus 2 is 3. 5 got replaced with 5 plus 2 is 7. 3 got replaced with 3 plus 2 is 5, etc. Since I defined my lambda addN, capturing capital N by reference, when I now continue on to slide 14, and I change capital N to -4, because capital N was captured by reference in the addN lambda, when I now do the same transform statement with addN as the function being applied, this time around, each value in v is going to have 4 subtracted from it, instead of 2 added to it as we had in the previous transform. And so now when I see my output from the red copy algorithm, sure enough, 3 minus 4 is -1, 7 minus 4 is 3, 5 minus 4 is 1, etc. And finally, one more time, I'm setting n to some different value. This time capital N is going to be set to 1. And when I do my transform, every value in v is going to have 1 added to it. So I now have 0, 4, 2, 1, etc. Okay, so that's an example both of using a lambda as the function to be performed by a transform. And in the lambda, we specified capture of this capital N variable by reference.